So he asked me to kind of gauge interest to see who would want to go. So that's my email address. If you guys are interested in going to a tour of the microgrid system and kind of checking out like applications of power systems here on campus, just shoot me an email and then I'm going to forward that to Tron with all the people who are interested in going. Yeah.
Let's do it.
This is especially very good for those guys that have power electronics too, because they use a lot of what you said in power electronics. They have an inverter, they have a solar panels, those kind of things. But in general, for those when they have this course also, it's a small power system. You have to get the system how it works.
This would happen when would it be?
It would be next quarter.
Thank you.
Just include our name, anything else?
Yeah. Probably name, major, year.
Okay.
Okay, quick announcement on the midterm break. You know, some of you are concerned about your midterm and you may want to drop the course. I'm suggesting to not do that, but it's your option. Based on what I hear from some of you, I think the last date you can drop the course is Monday. Am I right?
Yes.
Friday.
This week.
This Friday?
On his calendar it says Monday.
Friday.
If it's a Friday, it's a problem. I cannot give you the grade by Friday. But if it's a Monday, I was going to post the grade on Sunday. That was my plan, to put them there by Sunday, you know. Can somebody verify down quickly to see when it is, you know?
It's Friday.
Friday, I cannot do that. I'm going to be in Beaver, you know, from tomorrow, June, and no way I can grade the exams over there, you know. But Sunday, I guarantee you will have your midterm grade, you know. Hopefully, you don't want to drop it, but still, as I said, you know, hopefully the date will be Monday, you know, so you have time to see the drop.
It's November 30th.
Yeah. Monday? Okay, Monday. So that's good. So you will get your grade Sunday, you know, through email, you know. I'll email you with Excel sheet, and you will get your grade by Sunday night. I'm saying, don't drop the course, but because we have already wasted our time for the coming here to this class, it's too late for that. If you're going to drop the course, you should drop it first week. Not the 10th, but cannot do it, you know. You pay for the course, you waste your time, and it's going to delay your degree, you know, one more quarter maybe because of just dropping, you know. But I'll upload the grade your Sunday, okay? So you will have it. Yeah, I'll put the average there. I'll put the average there. It's simple. The Excel sheet just
Oh, you're with everybody. Okay.
yeah, we will put it with a student ID. You know, I'll put it with a student ID. And even now it looks like it's not legal. It still looks like I'm not supposed to send a grade to all the students with their student ID. You know, we want to keep the privacy, you know, for everybody. I asked them in my student time, they used to announce a grade like that, you know. But nowadays they are saying don't do that because some student they know the student ID of the other branch, and this way you know their privacy is kind of you know. But hopefully you guys will look at only at your grade, you know, don't look at the other grade. Okay, the last part we're going to talk about. I call it system modeling. I don't know, single line diagram, or we'll call it like a. I don't know, let's call it system modeling. System modeling. So by now, you know how to model the transformer, you know how to model the transmission line. Before going to the per unit system, if you go check your book, the one I give you is going to be in chapter 3 of your book. Let me see which page it is. Homework 5 is uploaded. Homework 6 will be uploaded tonight. And homework 5 next Tuesday. Homework 6 is Funke here? Yeah. Funke, can you announce a time, like in 1 hour, you know, span for Friday of the next week, you know? They can come drop their homework, you know, and you can pick up the homework. So Friday of the next week will be the due date for the homework number 6. Okay? And she will announce a place and somewhere you guys can put drop it. If you go check your book, one part I'm going to start to talk about it is the section 3.3 in your book. It's called per unit system. You know, We jumped down when we were teaching the transformer, and now I'm going to go back because I'm going to go through the pyramid system, system modeling, and some studies when you have a three-phase load or when you have a short circuit. See, short circuit also is we explained a single phase, but really single phase is not a concern in power system. Power system is a three-phase system. You know, we talked about how we can solve a three-phase balance system, right? If everything is balanced, now we are supposed to know how to solve that one. Short circuit also. Think about short circuit. Short circuit means when we have a three-phase system, A, B, C, and neutral, right? So short circuit means what? There is a maybe fault with a phase connected here, one phase to neutral, or to ground. Let's say the neutral is ground. Could be phase to phase short circuit, right? Phase to phase to ground. Could be three-phase short circuit, all these three connected together. Or could be three-phase short circuit connected to the ground, right? So these are all these various cases. The one is a phase to phase, or is a phase to neutral, or phase to ground. We're not going to talk about that. Because those ones, they are an unbalanced system. But when the three-phase short circuit happens, all three phases shorted together to ground, this is like a symmetrical system, right? So we are able to, we can analyze that. Those one is like a phase to phase to neutral, those kind of, they are unbalanced fault. We have to go through another chapter if you're going to teach that one. They call it a symmetrical component. How you can analyze an unbalanced three-phase system. It's not part of this course. We talk only about the three-phase short circuit, which is very, very often that one happens, you know, and it's almost the worst case to study for, you know, sizing your circuit breaker, those kind of things, because the three-phase short circuit almost is going to give you the maximum current in the circuit. So when you size the breaker in the system, you should make sure if the short circuit happens, the breaker is not going to blow off. You know what I'm saying? That's very important. When you size, that's part of our system of protection. If a short circuit happens, you don't want your circuit breaker boom blow up like a bomb, right? You want the circuit breaker to open the circuit. Instead of blowing up, you want it to open the circuit, right? You have to do some calculation. You calculate it for the worst case. You say this circuit is going to be worst case, I don't know, 10 kiloamps. So the circuit breaker I'm selecting, it has a 10 kiloamps in short circuit capacity. You know what I'm saying? The current rating is, I don't know, for example, 1 kiloamp, but it can break the short circuit current of the 10 up to 10 kiloamps. You know, that way, if you have that kind of short circuit, if you see that much current, the breaker is not going to blow up. It's going to open, you know, which is much better than blowing up the breaker. Just to let you know what the cost of this thing, you are talking about in millions of dollars. You know, this is not like $100, I don't know, $1,000, this kind of things. These are very, very expensive equipment. So you have to size them very accurately. You are not going to talk about sizing those things, but my point is, the simplest case we can study here is a symmetrical three-phase short circuit. First, we go talk a little bit about the generators, how we can model generators, especially synchronous generators, and very, very quick. We're not going to go in detail at all. Generators, we're going to discuss them. Synchronous generator is going to be in 121 next quarter. We go through the detail of the synchronous generator, how they work, how we can model them. But here, very, very, very simple model of the generator. You know, very, very simple model of the generator will be represented. So after that, I'm going to talk about the pyramid system, and after that, I'm going to start to model the system. I'll put a big system here. This is what you see with the single line diagram, all this, I don't know, STGNE, you know, document. We'll go through those ones. We start to analyze those kind of things, and after that, now I'll put some example. Hey, if there's a short circuit here, tell me how much, for example, short circuit current in the generator, for example, calculate that, and those kind of things. This is the last part of the course, and you're going to have one question definitely in the exam about this. If you learn it, this is the easy part. This is the easy part, you believe me, you know. If you don't learn it, this is a really difficult part, you know, to solve this kind of thing. But let's start with the generator. First, before we go into the variable system, most of the generators, this is a little bit old. No, we're not talking about the new one. We have a solar, we have a wind turbine. Let's go back like 25 years ago, 30 years ago. We were dealing with only synchronous generator in this system. Generators, they have a very very simple symbol. We use them like this. And this is a bus bar this generator is connected to. And here it could be a transmission line, it could be a load, whatever. So we have a generator, which is a electric machinery, is a rotating electric machinery. So this generator is gonna, if you are gonna draw an equivalent circuit for this generator, I'm going to the simplest model for this generator. This generator can have, for one phase I'm drawing. It can be modeled with this. XS, RA, EAF. And this is the BT. This is the one phase of this generator. It has a back EMF. They call it EAF. I'm not going to tell you how we can calculate how much is the EAF. As I said, we go through the detail in the next class, next quarter. Those ones who are interested, they can take that class and see how we can calculate this EAF. XS is the synchronous impedance of the generator. Synchronous impedance of the generator. RA is the armature resistance. So, as I said, I don't want to go through the details. So basically, a generator is a AC source, EAF, and an impedance is set. So there are two types of generators. There are two types of generators. They call it cylindrical the intention of this course is not to focus on the generator part, but we need to get a simple model for the generator. There is a cylindrical generator. What does it mean? All of you have seen electrical machine, right? They are usually cylindrical, right? You can see the outside of the motor. So basically, and they have, for example, a kind of base. They are standing here, right? The part is not moving. They call it a stator, right? This is a stator. The part is not moving, we call it a stator. The part is moving, we call it rotor. And then this one is called air gap. So if the generator is cylindrical, they're talking about the rotor. If the rotor is a full cylinder, it's a full cylinder. So the air gap everywhere is the same. This machine has the synchronous impedance of XS. There is an XS, X prime S, and X double prime S. Three values. And the R is see here we have armature, it has a winding and those kind of things. The R is the resistance of the armature, and usually in the power system, we say, hey, forget our armature. It's zero. So in this course, we assume our armature is zero, okay? So very simple, R is gone. Now, so what are these three values, Just to let you know how this system works, electrical flux is gonna go like this. And I said, we will talk about the detail of this thing in the next course, how this machine works. But my point is here, look at here, there is an air gap here, right? Remember how did we calculate the inductance for a transformer? L was equal to N squared over the reluctance, right? Think about it. Again, this is like a transformer. There is a one winding here and one winding here, right? The only difference is this winding is rotating, right? It's not a stationary winding. This winding is rotating. So basically, there is a kind of inductance, which is going to represent this back. So what is the XS, X prime X, and X double prime X? They call this one subtransient impedance. They call subtransient. They call this one transient, and they call this one a steady state impedance. So there are three impedances for electrical machines, the synchronous generator. Subtransient impedance, transient, and a steady state. So what does it mean subtransient and transient? So when you have a generator, it's working, there is no change, it's in a steady state. So a steady state, for example, this generator is giving you 10 kilowatts, 50 kilowatts, 1 megawatt, whatever, right? A steady is giving you this much of power, right? So basically, there is no change. The generator is rotating at a constant speed, there is no change, right? So the impedance is XS. Now think about it. Suddenly there is a short circuit, right? Somewhere we have either a phase to phase or whatever. We have a short circuit, any kind of short circuit. So this machine is going to kind of, start to mess up, you know what I'm saying? It's going to go either speed up or slow down. So the frequency is going to change. So the first two cycles, right after the fall, if we have a fall, up to 2 cycles or maybe 1 cycle after the fall, the impedance value is going to change for different reasons. I'll tell you one reason. One reason, when you have a short circuit, what do you expect to see? See? When you have a short circuit, you see a current like this. For example, you have a current like this, it's going to have a huge current, right? Either the circuit breaker, they're going to open the fault, or whatever happens, the current is going to go to 0, right? Here we were in the XS. During this time, because there's a huge current in the machine, the core can get saturated, right? That's one of the problems. The core can get warm. That's another problem. There are lots of unknown things can happen. So the impedance in this time is represented by X double prime X. They call it subtransient. Very, very short time. After that, from somewhere like this is a short circuit fault, this is a 1 to 2 cycle, and after that for like I think 2 to maybe 6 or 10 cycles, I cannot recall it exactly how many cycles, they call it transient. This is a transient. This is a subtransient. So during this time, the machine hopefully will get stable again. If it doesn't get stable, it's going to go away. The relays, they are going to separate the generator from the system. During this time, during the transient, the impedance of machine is represented by its prime. And if it gets to a steady state, this is the RMS value of plotting. This is the RMS value of the current. It was this much, suddenly we had a short circuit, become really huge, and it starts to come down, and it's going to get to the steady state value. During this time, is represented with X. So we have 3 periods: subtransient, transient, steady state. So it's enough this much for you guys to know about this. Hopefully next quarter we get time more to explain exactly how we can calculate this value. Even I'm not sure if we're going to talk about these two in the next class. These are pretty advanced topics, but XS definitely will talk about it, what it is and how we can calculate XS. So this is a cylindrical machine. There is another type of synchronous machine. Just I want you, when you read this problem, you read your book, you hear this name, just you have a picture of these machines in your mind. You don't need to know the detail of these things because that's a different course. This is a cylindrical or non-salient. They call it non-salient synchronous machine. Salient means everywhere is the same. There is no salience. But there is another type of synchronous machine. They call it salient pole synchronous machine. They are like this. If you look at it, again the stator is the same. This is a stator. All of you have seen electric machine, right? Am I right or not? Electric machine, you have seen it, right? Is there someone here who hasn't seen the electrical machine? Just I want to make sure you know when I'm saying this thing, yes, this makes sense. You haven't seen the electric machine? Let me tell where we can see this thing. Have you looked at the dyno of electric car? Not electric car, regular car. They have a dyno. All of them, they have a dyno. Do you have a car? Then I'm trying to find the example to tell you.
There's the motors in the lab, the trainer.
Oh yeah, the course you go over there. There's all those machines over there. They're electric machines. The power system lab. I think the electric motor they are there, right? This time you go there, at least look at the motor. You know, you go there, you can see these are small motors. These are like quarter horsepower, half a kilowatt, something like that. But they are all electrical motor or could be generator. If you look at, you cannot see inside, but you can see the outside. You know what I'm saying? Just look at it. You see that part outside is a piece of iron with some slots. I'm not gonna go into the detail because we are going to put a winding inside this slot. But I don't care about that right now. A stator. And there is one moving part inside the motor. You can see the shaft coming out of the motor, right? You can hold it and just rotate it yourself. If you had this little armatures, sometimes this little toys, for kids, they have a car. And there is like their electric car. Still, they have a small DC machine. It has a rotor and it has a stator, right? So the rotor could be cylindrical, or could be. I'm going to put the 2-pole machine, or it could be like this. So it's not cylindrical anymore, right? And this is a cross section of the machine, just I forgot to say. This is a cross section of the machine. Machine is like this. I cut the machine and I'm saying, look at me. They call this one salient pole machine. Salient pole machine. For this machine, there are two types of impedance. They call it XD and XQ. Just to let you know very, very quick, what is XD and XQ? What did I say here? I said here we have an impedance, inductance is because of this flux going through this air gap, right? Look at here, there are two paths. The flux can go this way. If it goes this way, the air gap is this much, right? But if the flux goes this way, you don't need to learn this, and we'll talk about this in a while as we go when you're interested. But I want you to know, just in general, you have a general picture. See here, there's a big air gap, right? Think about it, from here to here is the air gap. But here we have a small air gap, right? So there are two paths for the current. They call it direct access and quadrature access. So one of them, it has a smaller gap, one of them has a bigger gap, right? So basically, we are going to see two x's. They call it XD, XQ. Again, we are going to have x prime D, x prime Q, x double prime D, and x double prime Q. If you see these things in the questions, just I want to tell you what are these things. Prime means transient, double prime means subtransient, and without prime is the steady state. Okay? If I'll tell you, hey, I have a system like this, there is a load here, calculate, for example, I go to the voltage at the generator or something like that. So what value usually we use? I have a system, right? Let me put it here. For example, I have a system, there's a generator here, and this generator is connected here, and I have a transmission line here, another transmission line here. For example, I have a load here, and there is a for example, another generator here, and we have a load here, right? I'll ask you guys, hey, tell me how much that generator is giving me power, tell me how much that generator is giving me power, and how much this load is giving me. Which one of this one should I use? Either if it's cylindrical or if it's soluble. Which one should I use? Steady state, right? Because there's no transient, right? I'm saying, hey, I have this normal system is working, tell me how much this guy is giving me, tell me how much that guy is giving me, right? That's a normal condition. But now I'll tell you, hey, here there was a short circuit in this system. Usually we show it like this. Either I'll give you the value, you say hexagon, it's double prime, or prime. Or just I give you simply reactance, I'll give you one number, so just put that, it make your life easy. There's only one number, so you put that number and model the generator. But normally, if it's a steady state condition, we use the X. And if it's a short circuit or any change, maybe that's another thing. Hey, we have a load here, right? There's a load here. I'm going to bring this load 10 minutes later, right? This is again another change, right? It's going to create transient. Any change in the system is going to create transient. Short circuit is one of the worst ones. Think about it. It's a huge, huge change, right? But even load change can be transient, right? So basically, which one to use is based on the condition of the fault, condition of the load changing, what you have in your system. For you guys, it's going to be simple. I'm going to give you only one impedance in the system, in the question or whatever. So basically, use that number for modeling the generator. But when you get to the advanced power system and those kind of things, you see all these numbers. Okay, which one should I use now? So okay, let's see what's the condition. Oh, I'm in the steady state. This is a simple power flow. I use the X value. Oh, this is the short circuit. This is very critical. Because look at here, the current was like this, right? I need to calculate this peak current. This is very important, right? Because you want to size your circuit breaker. See, here usually there is a circuit breaker. Look at here. They show it like this. You don't want, for example, if there is a short circuit here, the current is going to come from here, the current is going to come from here, right? You want to size this one correctly. If it's a short circuit, I'm going to have this much of current, right? To calculate this much of current, I should put this value. To get the peak value, X double prime is much smaller than X prime and X. This is subtransient, right? You want to calculate the maximum current in the system. But in the steady state, you don't put that value because it's going to give you the wrong number, right? So my point is based on what condition you are. System is working normally, there is no problem, X. There is a short circuit, X prime. Another thing, overcurrent. What it's going to do to your system is going to make your system warm, right? As soon as you have a higher current, it's going to generator is going to get warmer and warmer. This is one example I'm saying. So maybe you should use X prime. Why? Because we said it's going to be there for 10 cycles, 15 cycles, right? The hexagon is not going to do that kind of damage because it's one cycle. After one cycle, the current is gone. But during the 10 to 15 cycle, it's a pretty long time. I want to see how much current is going through my machine and how much heat is generating inside my machine to make sure my machine is not burning, right? My point is, these guys, they have different application when you should use it. A steady state, short circuit, I don't know, transient, those kind of things. These are an advanced topic in power system or electric machinery. But in general, I want you to know, if you see these three values, myself when I was a student, my professor didn't tell us about this one. And always was a question for me, what's the difference between these values? You see, with this question. For example, if I'm giving you a short circuit study, I'll put it hexagon, X double prime. If I'm saying, hey, I have this load, I want you to calculate this value, I put the X value there. Always was a question for me, why this question is giving me X double prime, why this question is giving me X? Just I'm going to tell you, when you see this thing, you understand. A steady state, subtransient, and transient case. So, simply, we model a generator with a source and XS or X prime S or X double prime. This is the model for generator. Now, we know all the elements. The electrical motor, the same thing. We can model them the same way, electrical motor. If they are using the power, think about it. This is very critical, very important. You have a system. Let's say here you have a motor. Okay? Or let's say this is an electrical motor. We have a normal load. For example, let's say I have a resistor and inductive load here, right? How to model this thing? This is also very important. Think about it. If there is a short circuit, think about it. If there is a short circuit, usually short circuit current is much, much, much bigger than the normal current, right? You can see from the name, short circuit, right? If we have a load like this, what you can do? like this. Just like a heater or something like that. What you can do? Ignore it. Nothing. Look at it. I want to, for example, calculate the short circuit current for this generator, right? Some portion of current is coming from here, right? Some portion of current is coming up here, right? Right? Now, think about it. How big is this current? To compare to short circuit? Nothing, right? Forget it. There is no current. If it's a short circuit, you have a non-electric machine load. Non-electric machine load, keep in mind. Because the electric machine is different. So if it let's make it a little bit simple. I have a generator here, there is a bus bar here, there is a transmission line here, and I have a motor here. And I have electrical, normal load here, these are not a motor load, these are a regular load, something, right? And there is a short circuit, for example, in the middle of this line, right? I want to calculate the motor short circuit current and the generator short circuit current. Think about it. When the short circuit happened, first of all, forget this. You got non-motor load, keep in mind. Non-electrical motor load, right? They are like a resistor, impedance, those kind of things. No electrical machine. Then there is a short circuit. Do you think still the current is going to go this way? The motor is going to act like a generator. Think about it. This motor is rotating, right? I told you the motor is, the only difference is like this. Look at here. Just I'm going to put in the model here. I have another generator here, and this is my transmission line. This is my generator, right? And this is my motor, right? And let's say right in the middle, I'm going to model it like this. This is my transmission line. Here there is a short circuit, right? So generator is generator. The current is going to go like this, right? The current is going to go like this. The motor is electrical load, right? But rotating. This machine is rotating, right? There is some back EMF. When there is a short circuit, this guy starts to give the power to this way. It's going to change the mode from motor to generator, right? Because there is a perfect short circuit here, right? So the motor starts to lose the energy. It's going to act like a generator. Think about it. I'm going to give you another example. How many of you have heard about the regenerative braking? Where do we use them? Car. Can you tell me what's a regenerative braking?
The motor generating power when it's not being supplied with power.
The motor generating power, when do they, for example, regenerating happen?
You stop supplying your current.
No.
If you close the throttle, it's still moving.
It's using the rotor still spinning from the force of the car moving, using that magnetic field to recharge it.
Not moving.
Well, when the car's moving, doesn't it use the alternator to charge the battery?
That's something else. But let me tell you this: regenerative brake. You hear you will hear about it a lot. But all these electric cars, hybrid car. I'm not sure how many. I don't have electric car, but I don't know exactly how it does. But some of you may have drive. You may drive electric or hybrid car. There is an electrical brake, and there is a mechanical brake, right? If you go, for example, drive Prius, you see you can brake the car. Stop the car by mechanical brake, like a regular car. You push the brake, paddle and stop the car. But if you are a good driver, you shouldn't use that one. Usually young people, they are not that patient. They go stop, start, stop, start. But if you are a little bit older, like me, you are a little bit, you're cautious. You see for example, the lights, signals like 200 meters away, and you say, oh, it's yellow, let's slow it down. You know what I'm saying? The car is going to slow down, and you push this electrical brake. What is going to happen? See, your car has some energy, right? So to stop it, you have to take that energy out, right? This energy is in the electrical motor, it's rotating, right? It's moving the car. If you start to take the energy out of the car, what is going to happen? The motor is going to start to slow down, right? So basically, the motor is not anymore motor, because you are taking energy out of the motor, right? The motor becomes generator. They call it regenerative braking. The motor acts like a generator, to stop the motor, either you can put a kind of mechanical brake on it, stop it, burn all the power and dissipate all the power, or you can use the electrical brake, take the energy slowly out of the motor, put it in your battery, restore it over there and use it again. So that's the difference, when there is a hybrid car, they cannot for sure give you a MPG. They said the MPG stand is based on the driver. If you are a kind of good driver, you may get up to 55 miles per gallon. But if you are like a stop-start driver, maybe you drop to 35. If you think about it, how much is different, So it's very important to use those energy, So basically, take the energy back to your battery. So here the same thing. This machine was motor up to a few seconds ago, right? Now, here there is a short circuit, right? And this is a voltage source, right? Because this is a rotating machine, right? It's going to generate back EMF. So now there is no more energy coming from here because all the energy is going to this point, right? So this guy will start to give the energy back to here until it stops, right? So the motor is going to, during the short circuit, the motor acts like a generator. Just keep in mind. I may use this one in the exam, just I put the motor there and I say the short circuit, you should treat it like a generator. Got it? During the short circuit. So now we know enough about the synchronous machine, how do they work, a little bit how we can model them, during the short circuit, how we can model them. Now let's go to the per unit system. Per unit system. Remember how painful it was when we were talking about transformer. We said, okay, is this even at the secondary or is it in the primary or high voltage or low voltage? Everything was depending which side of the transformer you are, right? Because here the nominal current is 100 amps, here the nominal current is 10 amps, right? So that's all. This still causes problem in calculation because one side voltage and current is different from the other side because of the turn ratio. Right? So, this is the one main reason to use a per unit system. The other reason is, so you can see this transformer has an impedance of, for example, 10 ohm. I'm talking about R equal X equal. Or this generator has an impedance of, 20 ohm. That generator has a 30 ohm. This transformer has a 2 ohm. They are all different numbers, right? You can see very different numbers. But when you put them in a per unit system, is a percentage one. It's very narrow. Usually a few percent. The impedance is a few percent. 2%, 3%, 5%, something small, like 8%, not more than 10%. You know what I'm saying? The number you can see is going to be in what range. But maybe you have a motor, it has a 10 ohm resistance, another one is the 0.1. Just I want to show you, when you see this number, it doesn't give you any physical meaning. Is this one large or is it small? Per unit system give you a little bit better physical meaning. Oh, is it 1%? Is it 2%? Right? So always, percentage wise, for example, I'm going to compare 3 of you to myself, for example, I have some money in my pocket, I'm not going to say how much. But you say, oh, this guy has nothing. I don't have anything. But I'm not a cash person. But so, for example, say this person has a $10. How much compared to me do they have? You know what I'm saying? No idea, right? You say this person has a $50. That person has a $200. So comparing to me, you don't have an idea. Okay, this one has a lot of money or not. This one has a lot of money or not. But when I give you the percentage, you say, hey, I have some money, but this guy has a 10% of my money. He has a 20% of my money. You know what I'm saying? He's going to give you more physical control. I know how much this one has, how much this one has, percentage-wise. You know what I'm saying? He's going to give you a little bit more meaningful number. Per unit is exactly like that. When there is a percentage, so we'll get, okay, how? I can now see this generator has a 5%, this generator has a 2%. So basically, oh, I can see this generator is this one with the 2% is better than this one. Why? Because remember we said if this one is going to be ideal generator, if this one is an ideal generator, how much is this? 0, right? Because you want this voltage to be fixed, right? But if this one has some value, when you have a current injecting, you are going to have some drop voltage here. So basically the voltage here is different, right? If this one is 0% is ideal generator. Always you see the fixed voltage, right? So if you have a smaller impedance, the better. Your generator is more ideal, right? Remember when we said we parallel the transformer based on what is the ratio of their per unit impedance? They are going to share the power. If you go back and look at your notes. So that was exactly it. Maybe this transformer has a 5 ohm, this one has a 20 ohm. But if you put them in their base value, this one is 1%, this one is 5%. Yes, look like this is 10, this is 15, this 50 is worse. But based on their rating, this 50 ohm is 2%, this 10 ohm is 10%. So that 50 ohm is better transformer. You know what I'm saying? So Very is going to help you in 2 ways. First, we're going to start to explain it a little bit more. Help you with this transformer problem. High voltage, low voltage size, the values they are different. We are going to have per unit. Everybody is the same. The current is 1 per unit. If in the secondary the current is 1 per unit, in the primary the current is 1 per unit. So it's going to help you with that to make your calculation easier. Also, it's going to give you better physical meaning on the impedance of the system. For example, about the generator is 2%, 5%, 2%. It's not going to be 100 ohm, 1 ohm, something like that wide. It's going to be very, very narrow range, less than 10%. It's going to give you a better meaning about this kind of thing. But let's start to see how we can unitize the system. A single phase transformer I have. I'm going to start with a single phase transformer, and after that we're going to go to 3-phase system. Hopefully we'll go through one example in the discussion. Look at it. I'm going to start with a single phase system. And I'm going to start with a transformer, which is the most difficult one. No, the rest is very simple. Let's call this side V1, V2, N1, N2. Right? Usually we select the nominal value of the transformer as a base value. And there are 3 parameters, 3 independent parameters. We have a current, voltage, apparent power, and impedance. 4 parameters. So, they are not independent from each other. There is only 2 independent parameters. Why I'm saying they are not independent? Look at here. Z is how much? Is V over R, right? S how much is a VR? Apparent power I'm talking, right? So if these 2 I have, I can calculate the other 2, right? I mean, when I'm saying they are not independent from each other, I cannot have 4 different values, 4 arbitrary values for example, I, V, S, and Z. I cannot have that. If I have a 1 here and 2 volts here, can I have, for example, for S like a 10? No, I cannot. So these are not independent variables. My point is, this one is 2 times 1 is 2. Has to be 2. How much is this one? 2 divided by 1 is 2 ohm. So they are not 4 independent. They are 2 independent variables, right? Out of 4, you can select only 2. The other 2 will be calculated. You can select whatever you want as a base, but usually they select voltage and S as the base value. So we say V base is Vn and S base is Sn. N is nominal value. Let me put a little bit more here. For example, let's say we have a transformer is 110 to 220 volts, and S is, for example, like 5 kVA. Right? 5 kVA. So, if I am in this side of the transformer, say this is the primary, and this is secondary, right? If I am in the secondary, how much is the nominal voltage? V2 is how much? 220. Basically, I select my V base on this side. How much? 220. How much is my S base? We said the nominal value. Is it important which side I am? No, doesn't matter. How much? 5 kV. But how much is the V base in the primary? How much is the V base in the primary? Let's call this one V base 2. How much is the V base 1? Is the V base 2? Is the V base 1?
1/2.
So V base 1 is going to be V base 2 times basically the N1 over N2 also, right? Times N1 over N2. The ideal transformer equation, right? N1 over N2 is how much? 110 over 220 is 0.5. So basically it's going to be 0.5 V base 2. Right? How much is it in this case? It's going to be 110, right? But how about S base in the primary? The same value. S base doesn't matter which side you use. Now, let's calculate the I base on the primary and secondary. How much is the I base here in the secondary in general? Before getting to this problem, I base is going to be S base over the base. So, how much is in this example in the secondary? It is a 5,000 over 220. I don't know how much it's going to be. So, I calculate my base value on the secondary. How much is the I base 1? Right? So for any three-phase or single-phase system, there are 4 variables: voltage, current, S, and Z. We select 2 of them as a base, usually S and usually V. And we select the nominal value, usually. You can select whatever you want, but it's better to select the nominal value. We select the nominal value as a base value. After that, we can calculate the I base value. And how about the Z base? How much is the Z base? Is a V base divided by I base, right? I'm going to solve one example. You will learn it better. We'll go with the one example. Yeah.
Can you explain what this base means, or you know?
Base is base. Actually, it's base. No, let me go through
So
one
you-
example.
so you just
get
call
the
one-
equation. You are defining a. For example, here in the currency, we said dollar is the unit of the currency, right? Now we said you have 100 units. Yeah, 100 units was how much? $100, right? That's a base. You selected something as a unit, and now you represent everything based on this unit.
So you call one side like the base one, and
Yeah.
the other one is.
But I'm saying I'm gonna go through examples. You know, with examples you will learn, you will get it better. So Z base is the V base over I base, right? Now let's replace I base from here. It's gonna be V base over S base over V base. So basically the V base to the power of 2 over S base. Again, you can calculate the Z base in the primary of the transformer. If you are in the primary of transformer, how much is the V base? It's going to be V base to the power of 2, V base 1 to the power of 2 divided by S base. If you are in the secondary of the transformer, it's going to be V base 2 to the power of 2 divided by S base, right? Now, let me give you one example about this. Let me go through one example quick here. magnetization brand. RCXM gone. We don't consider it. R usually gone. We don't put the R. Only we keep the X insert. Usually it's like that. Or I give the example for the discussion, because I want to finish the three-phase also. So very simple. Again, go over it. In every system, you usually select single phase, V base and S base as a base value, and after that you calculate I base as a S base over V base, and the Z base is going to be V base to the power of 2 over S base. Basically, by selecting these two, you can find the I base and Z base. Now, if you are a three-phase system, three-phase, this is a single phase. If you are a three-phase system, again, we have 4 parameters. We have V, I, S, and Z, right? Again, we select the voltage and S as a base value. V base is going to be VLL nominal. We select the line-to-line voltage as a base value. Nominal line-to-line voltage. And for S base, we select S3 phase. You know, for example, we said we have a 3-phase generator, 100 MVA. That one is going to be our base. We select that one, S3 phase nominal. So if you have this one, how much is the I base? Can you tell me how much is the I base?
That's 3-phase part.
Right? If you remember, we said S is VL, sorry, the square root of 3. Just keep in mind, the square root of 3, VL, IL, right? So IL base is going to be S base divided by a square root of 3 V base, right? Let's go for the impedance. I'm going to do the calculation here. Basically, Z base is going to be V base over a square root of 3 divided by I base. Why I put the V base over a square root of 3? Because this is line voltage, right? Line to line. I should come to the star equivalent. So for example, I have this one, look at here. For example, I have this one. I want to know how much is the Z base. I want to know how much is the Z base. I know this voltage, right? I know this current. But if I want to figure out this one, it should be this voltage divided by a square root of 3 to get this voltage, right? Divided by this current. Now, let's replace I base from here. Let's replace I base from here. So Z base is going to be so it's going to be V base over square root of 3 S base over the square root of 3 V base. This one and this one are going to cancel out. It's going to be V base to the power of 2 over S base. See the same equation we had over. Z base for a 3-phase system is going to be V base to the power of 2 over S base. But keep in mind, V base was a V line to line. S base was a 3-phase system. Okay? Now, this is all about the parity system. Now I'm going to start to go through examples. You know, I'm going to start with a very simple example. Use this equation to get to the basic of this one, and after that we'll get to a little bit more complicated. The teaching is over. But now I'm going to go through examples. Today, rest of today, and next week it's going to be all examples. But you will learn this one, what does it mean? Okay, let me start one example here. I'm not going to go through a single phase, because maybe later I'll do a single phase. But I want to start with a 3-phase system, This one is going to be design homework number 5. Maybe start with a little bit simpler one. Let's start with this example. This is a pretty simple example. Oh, something. Oh, we will talk about that. Well, let me say that one to make sure all the course I'm going to teach you over. Now we have some values in the base. Let's call it old base. We had some voltage and current. For example, I have selected 10 kV, 100 MVA. Now I have all my values in this system, based on this system. Somebody comes and says, hey, I'm going to change the values. I'm going to select 100 kV, 10 MVA. What are the new values? I want to find out, I have an old basing system. I'm going to come calculate the new basing system. So let's call it here. Z base new. This is also important. It's going to be, I'm going to write the equation and after that I'm going to prove it. It's going to be Z base old. Old means what you had before, whatever was before. You know what I'm saying? We had this base system. Now we are going to get to this new system. It's going to be I think it's going to be, don't write this one out, let me check it. V base new over V base old to the power of 2 times S base old S base. This is Z new. Whatever was in that case, Z times Z. Just let me make sure the equation is correct. I can tell you how we get there. I'll explain the proof, next week. You know what? Just let me make sure. This one is very old order. Now, give this equation, I'm going to solve some examples to see what does it. Let's start with an example from the book. This is a simple single-phase system that we start with. It says we have a system like this. We have a system, there is a generator here. It's a single-phase system. Let me see. It's a circuit or yeah, this is a single-phase system. I have a generator here. This generator is connected to a transformer. This transformer is connected to the transmission line, X line is 2 ohm. And this one again connected to another transformer. This is the transformer T1. This is the transformer T2. And here there is a load. So let's write the load. Load is 0.9 ohm plus J.2. This transformer is a 460 volt to 115 volts, and x equal is 0.1 per unit. This transformer is a 30 kVA, oh, the kVA, this one is 20 kVA. 20 kVA. This transformer is a 30 kVA, 240 to 480 volt, and x equal is 0.1 per unit. This generator is an ideal generator, and the VF is 220 with 0 angle. Usual generators, they have an impedance, but in this example is a parity. It says we have a system like this. This is a single phase system. As I said, in power system, usually we don't deal with a single phase system, but we start with an example and we go to the 3-phase. We have this system. It says using, see, keep in mind, it said using base value of 30 kVA and 200 volt in zoom. He called this one zoom. Let me put it here. He put this one as zoom 1. Let me put it here. VS was 220 with a 0. He called this one zoom 1. He called here zoom 2. And he called here zoom 3. It says, see, this is what the example is giving us. It says select the base value of 30 kVA and 200 volts in zoom 1. It says, I want you to select V base, how much? V base 240 volts, and S base, how much? 30 kVA. Here, it gives us this value.
Sorry, what does it say under the second transformer? It's 20K.
20 kVA, 460 volt to 115 volt.
Thank you.
So it says they're on they call it, impedance diagram or single line diagram of the system. They call it per unit impedance diagram or per unit single line diagram. I want to draw the per unit system for you. This system is not per unit, If in a per unit, it shouldn't be ohm. It should be percent. Everything should be percent. So we have this system. I want to calculate I'm going to add one more thing. Calculate the current here, here, and here. We're going to calculate current on all three zeros, right? In per unit. First in per unit. After that, you want to calculate the real value of the current. You can add this one to the example, I have a system like this. First, draw the per unit single line diagram. Not single line, this is a single phase system. First, draw the per unit system. Second, calculate the current in all three zones in per unit system. Third, tell me how much is the real current in amp. So we are going to calculate this. This is a very good example. And it tells us to select the base value this much here, in this zone. The first thing we should do, we should find out how much are the base value in the other zone. Let's see how much is the base value here. If this one, the voltage here is 240, how much is the V base here? Can somebody tell me? How much is the V base in the middle, in the zoom 2? I know the V base is 240 in zoom 1. How much is the V base in zoom 2? How much? 480. Use this ratio. This is easy because 240 to 480, you can quickly say. But if this one was 220, right? What you should do? You should time it 220 times 480 divided by 240, right? So V base is how much? Let's call it, I'm going to put it V base 1. S base, I'm not going to give it. This is a V base 2. How much is it? 480 volts, right? How much is the S base here? S base from here to wherever you go. There is no change. S base is going to stay the same. How much is S base? It's going to be 30 kV. How much zone 3? How much is the S base? 30 kV. Right? How much is the V base here? How much is the V base here? It's going to be 150 over 460 times V base 2. Correct? So it's going to be 115 over how much? 460 times 480. I don't know how much it is. Can somebody calculate this quickly? One? 460. Right? Can somebody calculate this quickly?
120. 120.
120. Yeah, 120. Now, let's calculate the rest of values here. Basically, we should calculate how much is the ZB1? Huh? 60. So, how much is the ZB1 in this area? How much is the base value for the impedance? How much is it? V base 1 to the power of 2 over Z base, S base, right? So basically, it's going to be somewhere. I need some help here. 240 to the power of 2 divided by how much? 30 kV. Can somebody calculate this one? How much? 1.92 ohm. How much is the I base here? Right? So how much is the S base? S base is a 30 kVA, right? Divided by how much? 240. 125 amps. Let's calculate them here. How much is the Z base here? ZB2. It's going to be 480 to the power of 2 over 30k. Huh? 7.6. Yeah, 7.68 ohms. How much is the I base 2 here? This one divided by this, right? It's going to be 30k divided by 480. 62 and a half. Let's come here. Let's calculate them here. How much is the Z base 3? It's going to be 120 to the power of 2 divided by 30. 0.48 ohm. How much is the I base 3? amps. Okay. Now I have all the base values. I'm going to calculate the per unit value.
So for the base, all the base values we're calculating, that's independent of all other like losses and
Only based on difference. See, it told us how much is the V base here. I calculated V base everywhere, right? And S base everywhere is the same. Now let's start from here. What I can per unitize here? Do you have the impedance here to vary with it? Only thing that I have is source, voltage, right? So I'm gonna have a source. How much is this voltage? Is gonna be, how much is the base value here? 240, right? How much is the voltage here? 220, right? So basically this one is gonna be a source of 220 over 240 with 0. What's the unit for this voltage? There is no unit. Why? Because I divided by voltage, right? Everything is going to divide it by its base value. If it was a real generator, I should have an impedance here, right? So for example, let's say I have a 2 ohm impedance here. I'm not going to put the 2 ohm. I'm going to put how much? 2 ohm divided by 2 ohm. So it's going to be 100%, right? 2 ohm over 2 ohm is I put 1 or 100%. So but I don't have that. So I have a generator here. Now, how about this transformer? See, the value we gave me is a per unit already. Is a per unit already. This per unit value for any transformer, any generator, is based on the rating of the machine. Remember here I said how we select it? So basically, this value is the per unit impedance of this transformer in this space. Right? In this space. Now, if I want to calculate the new per unit value, for example, let's say select either here or here. Do you want to do it in the primary or in the secondary of the transformer? Let's do it both. Let's do it both sides, right? I want to calculate the new impedance of the transformer in the per unit system, right? Before doing that, I want to do a little bit more work here. We don't need to do that, but I'm going to just, because this is the first time we are going through this per unit thing. How much is the real value of the transformer impedance? If somebody asks me, is the 0.1 per unit, or they say 10%. Usually they say percent, 10%. So how much is the real impedance of this transformer? Okay, this is talking about the real value. Now it means which side, primary or secondary, right? Per unit doesn't matter, either primary or secondary. Let me tell you how much is the, if we want to consider this impedance in the primary of this transformer, I'll tell you how much is the real value. I'll call it X at P1, primary of number 1. So how much is the base value, Z base, on the primary of that transformer?
1.9.
See, XP1 is going to be X per unit times Z base in the primary. So I know X per unit is how much? Is 0.1. How much is the ZB1? How much is the base value of this transformer in the primary? Remember we said for a single phase system, it's going to be V base to the power of 2 over the S base, right? How much is the V base on this side? Forget this orange number. These are the new base value. Just look at this transformer isolated. Just this transformer. Look at this transformer with this number. Forget the rest of the system. Forget the rest of the system. Because this number is only based on this case. So how much is the per unit value of the, so how much is the base value of impedance in the primary? It's going to be VB to the power of 2 over S base, right? How much is the VB? 240. How much is the SB? 30 kV, right? So basically, it's going to be 240 to the power of 2 over SB. And how much was this? For the transformer, the value is in the black circle, is 30 kV. But if I were to calculate this one on the secondary of the transformer number 1, this one is going to come with some number. It's going to be some number, right? But somebody, hey, no, I don't want to calculate the impedance in the primary. I want to calculate the impedance in the secondary, right? How much is the V base here? 480. calculate that one for me would be great. So it's going to be experiment again times ZB2. Guys, don't get confused with 1 and 2. These are not this purple one. These are not this purple one. Forget this purple one. I'm just talking about this transformer alone, right? I'm just talking about this one. I have one transformer here. Just let's put it this way. I have a transformer is 240 to 480, 30 kVA, 0.1 per unit. So I have this transformer. I want to know if I want to model this transformer with a real impedance in the primary. How much is that value? I calculate this. I say X per unit times Z base on this side. If I want to know how much is the impedance in the secondary, it's going to be X per unit times Z base in this side. So in this one is going to be 0.1. How much is the Z base in this side of the transformer? 480. How much is the voltage base here? 480. So basically, you can model this transformer. Did somebody calculate this number?
First one 0.9.
How much is the first one? Tell me.
0.992.
Say it like loud. Huh? I'm going to talk like you guys next time. You know, I'm explaining to you. 0.1920. How much is this one? 0.768. So basically, if I want to model it like this, I have the ideal transformer here and this much impedance. But if I want to model it like this, I put the ideal transformer here with this much. If you guys didn't make a mistake, this one should be right? If you didn't make a mistake. Look at it here. Either you can put it in the primary or you can put it in the secondary, right? I move this one from this side to this side. What should I do? I should divide it by 480 over 240 to the power of 2, right? So either you can model it like this, or you can model it like this. Or, think about it. So now I say which one? Or you can say, hey, this is my transformer. Which one is it? This one is here, right? It doesn't matter which side you are. So we have a transformer. It has a 0.1 per unit impedance. Now, in this system, in this basing system, I want to find it in the new system. Either I can use this one or this one, whatever you want. There is no difference. So if I want to calculate the transformer T1, it's going to be like this. I'm going to put XT1. In the new base, how much is the XT1? I'll use this equation. How much was my per unit value? How much was my per unit value? 0.1, right? 0.1. Which side do you want to do? You want to do it as right side or left side? Left side. Let's do left side. So I should put the V base old. Old is the rating of the transformer, right? How much was the V base old? 240, right? How much is the V base new? The purple one, right? The purple one is the new value, right? How much is the V base new? 240, right? Times S base new. How much is the S base? S base doesn't matter where you're selecting, right? How much is the S base? 30K, right? Divide. How much was the S base old? Old value?
30.
How much? 30. So basically in this case, it's going to be 0.1. It didn't change. Because the values we selected, they are the Nominal value of the transform. The value they selected there, the same with the nominal value.
How's the new base voltage 240?
Huh?
Why is V base U 240?
I asked, which side do you want to do? Left side, you said, right? See, this is the old value. These are the old value inside this black circle, right? How much is the V base here?
Oh, okay.
240. How much? These are the old value. How much is the S base? This one. How much are the new value in this side? See, the problem told us 240 and 30K. No, by the way, you are done with the teaching. This is kind of like a, what do you call it? Problem solving session. We're going through that one, you know. Now, let's get here. I want to count. I should put a per unit value for this one. How much is the X line? How much is the X line? How much is the X line? Somebody tell me. This is 2 ohm. How much is the base value? 7.67. So basically it's going to be 2 divided by 7.68. Somebody calculate it for me. How much is it? 0.260. 0.260. Okay, per unit. See, per unit. These are all per unit. There is no ohm, no ohm anymore. Now, let's get to this transfer. We are going to model this. Left side or right side? Which one do you want?
Right.
Right side. We are going to go with the right side. XT2. We know the old value. I'm going to put it here. XT2. How much is, based on this equation, how much is the old value? See, again, put it on this black circle. These are the old value we have. Right? How much is the, we said right side, right? How much is the X? 0.1, right? Times. How much is the V old on the right side? 150. How much is the new base on the right side? 120. Times S new. How much is the new value on the right side? 30K. Right? And how much is the old value? This is the old value, right? Good. And somebody calculate this one too. Point 1 3. Very good. Let's get to the load. How much is this one? 0.9. How much is the base? 0.48, right? So this one is going to be how much? Sorry. This one. 0.9 divided by 0.48. And the other one is 0.2, right? It's going to be J 0.2 divided by 0.48. Guys, tell me what how much is it? Please calculate. Is it 0.4167? Just 0.17. 0.9 over 48 should be 2 almost. A little less than
1.85 or 1.87.
1.87 per unit. Right? And tell me how much is this one? 220 over 240. 0.917. So I'm going to redraw my circuit again. this one is 0.970. I have a xt1, j.1. I have a j.26. I have a j.138. I have j.417, and I have a 1.87. So this is a current in a system. See? The beauty of this system, is there any transformer there? No. So if I calculate the current in the load side, this is a per unit. Keep in mind. Whatever we are calculating now is per unit. If I calculate this current, for example, let's say I calculate, so this current, how much is it? It's going to be, I is going to be equal to 0.917 with 0 divided by all these things add together, right? It's going to be j.1 plus 0.26 plus 1.38 plus 0.417 plus 1.87, right? This is a very simple calculation. We can calculate this current. Let me see, do I have an answer here? I don't think so. This one calculated that. Calculated, looks like it came down with I load is 0.4395 with minus 260. If you calculate this one, looks like the answer is no. Now, this is the period. How much is the current getting from the generator? Real current. The basic current we know everywhere is how much? 0.4395, 0.44, right? Per unit, everywhere. But how much is the real generator current? How much is it? Here. How much is the real current here? I call it I generator. I'm going to call it I generator. Oh, I call it I source. How much is the I source? I base on the generator side times this. How much is the I base over there? 125, right? 125. This is the I base. Remember, this is the I base. Times that. I'll put it 2.44 with minus 26. This is the amp. The answer is going to be amp. How much is the current in the secondary of this transmission line, this transformer, or in this transmission line? How much is the real current? I call it IF, I current. How much is the I line? I know the per-unit current here. How much is the per-unit current? 0.44, right? See, this is this one, right? How much is the current here? 0.44, right? How much is the base current over there? 62.5, right? So it's going to be 62.5 times 0.44 with minus 26. How about the per-unit current in the load side? How much is that? Sorry, the real current in the load side. I load is going to be, how much is the base current here? 250, right? 250 . is of area. You know the current in all the system is 0.44 per unit. Now if you want to know how much is the real current in that point, you go check how much is the I base on that point. Time it by this per unit value. Okay, I'm going to go to this is single phase system. We can do the same thing for three phase system. Get like 5 minutes break, and we'll go through one more example. Or if you don't want to get a break, we can go and we can stop after that. Which way do you want? I'm going to go through one more example. Okay,
You guys finished class? Yeah. When I read explain everything. Explain everything.
Yeah, but we want to say I gotta put it in because that's the show that is 11.
voltage generation, 11 kV is not high enough for transmission line. They put a kind of a step up, transformer to step up the voltage from 11 kV, maybe to 66, 130, 260, whatever kV. So, and usually here there is a breakers. See, in this example it doesn't say, but there are breakers that this square there is showing a breaker. The worst case can happen. The worst case can happen. It could be a short circuit here. Why I'm saying the worst case? Can somebody tell me why? Let's say this is a transmission line. I think you have it in one of your homeworks. You'll run the homework problem. Let's say this is a transmission line like 10 kilometers or 100 kilometers. The short circuit can happen here, but the worst case is here. Why?
Because you're getting maximum current.
Because we still have some like
Impedance.
impedance on
So here you have some impedance added here, right? Basically, if you are going to calculate the short circuit, you are going to take this voltage divided by impedance of this one plus impedance of this one plus impedance of this one. That would be the short circuit current, right? But if it's right here, this one is gone. You don't have any impedance. And usually they are low impedance this way, it's going to create a huge current. Now, we have a system like this, two generators connected to this bus bar. This bus bar connected to a transformer, low voltage to high voltage, and there is a short circuit at the terminal of the high voltage of the transformer. We want to calculate the current. Yes. We want to calculate the fault current for each generator. How much current we have here? We call it fault current. How much fault current we have here? So, the generator, this is the information of the generator. Let me write it here. It says G1 is generator 1 is rated 60 kVA or 60 MVA. 11 kV. And X double prime of 25%. They put it this way. Usually they put it right percentage. G2 is 30 MVA, 11 kV, and the same, 25%. Then the transformer is 90 MVA, 11 kV to delta to 66 kV stop. Is kV. And the X is 10%. So, here we don't have a system. We have a system like this: generator 1, generator 2, and transformer. How much is the fault current for each transformer? First, we need to draw the reactance or impedance diagram for this system. Let me draw that one first, and then I'll get into the rest. So basically, it's going to be like this. This is generator 1, right? Here, generator 2, here is going to be these two connected together. And to model this one, we can put it like this. And there is a switch, we are closing this one, right? This is a short circuit. And remember, we said when there is a short circuit, basically there was some current going this way, right? So when there is a short circuit, let's forget that one, right? So basically it's going to be like this, the transformer, and here is going to be like this, right? Or if you want, you can put these two also connected here. And this is a single diagram of this system. Now we need to calculate all this value, put it there, and calculate the short circuit current. So, in the exam and in the homework, usually I'll tell you where to select the base. But if you are an engineer yourself, you are solving this one, you can select the base wherever you want. You know what I'm saying? You can select the base wherever you want. But usually in the question we tell you, because if I don't tell you, everybody is going to get a different answer. Because you can select the base here, you can select the base here. So all of you can do the right calculation, but the numbers are different. I want to fix everybody to get the same answer if they're solving it correctly. We still select the transformer nominal value as the base, right? I'm going to select the transformer nominal value as the base. Basically, how much is the S base? 90 kV. 90 MV, right? I select the transformer nominal value as the base. So, if I select this one, how much is the V base in this side? 11 kV. How much is the V base on this side? 66 kV, right? So, I select the transformer as the base. So, how much will be the new impedance of the transformer? So that equation. It's not going to change, right? Because the old and new, they are the same for transformers, right? We selected the transformer value. Now, this is the base. So I'm going to select S base. And V base, let's call it here 0.8. Let's call it 0.8. V base at 8. How much is it? How much is it? 11 K. Right? 11 K. Now, also something else is said in the problem. It says, let me see here. It says, this one, keep it, this is very important. Before a fault occurs, the voltage on the high voltage side of the transformer is 63 kV. The voltage before fault here, VB. Also he said VB before fault. Before fault is how much? 63 kV. Right? 63. And the other thing is saying the transformer is unloaded. This is all before fault. You know, we are talking about the before fault. Before fault, this voltage is 63 kV, and the transformer is unloaded. So this is for the fault, right? Forget this one. When he said unloaded, how much current we have displayed? 0, right? Unloaded. And we don't have the magnetic branch to be worried about that. So how much is the current here? 0. And also it says there is no circulation current between the generators. What does it mean? When there is no load, who check the circulation current for transformer? There is something here. It said there is no circulation current, right? This is all just simplify this problem as much as possible. Basically, if the transformer doesn't have any load, means here the current is 0. If there is no circulation current, how much current we have here? 0, right? So if here is 63, how much is here? How much is here? 63 times 11 over 66, right? So you see maybe 10 kV, something like that, right? If here is 10 kV, look at it, if here is 10 kV before fault, I'm talking about before fault, see? This is the before fault. Here is the 66, 63, right? Here is going to be maybe 10, so basically 63. We're going to talk about this one. Here is going to be maybe, I don't know, 10 over 11. And if there is no current, how much is this voltage? How much is this voltage? The same as here, right? If there is no current, the same as here. How much is the delta for this one? If there is no power. Remember just I told you, last Saturday. We said P is equal to Vs, I don't know what I call it. Vs VR over X sine of delta, right? Right? So if P is 0, there is no load, right? P is 0. Vs is this voltage. VR is this voltage, right? X is this value, right? So this voltage cannot be 0, this voltage cannot be 0, this one cannot be 0. How much is the delta? We say P is equal to Vs VR over X sine of delta, right? P here is how much? 0, right? This voltage is something. This voltage is something, right? This X is something, right? So basically, if this one is 0, delta has to be. So basically, both of these two, they have 0 angle before fault. See, this is very important what we say. Now let's prioritize this system. Let's prioritize this system. One more time. It says before fault, transformer is not loaded. There is no circulation current between the generator. Now, the transformer is no loaded, and there is no circulation current between the generator. And we know the high voltage outside of the transformer is 63 kV. Now let's say if there is a fault, how much is the generator fault? Each generator, how much the current generator has? Let's calculate. Okay, let's call this one xg1, xg2. I'm going to call this one vg1, vg2. It's the xt. Let's put it here, before fault. How much is the vb? Right? So how much is the VB period? How much is the VB period? We said we are going to select the transformer value as a base for the system, right? I'm selecting this one as the base for the system. So how much is the V base here? 66, right? So before fault, how much is the VB per unit? And let's assume here is that I'm going to select this one as a reference. This is 0 angle, right? I don't know how much it's going to be, but it's going to stop, right? Let's calculate. .955 with a 0 angle, right? So, how much is the VA per unit before fault? I'm talking all about before fault. How much is the VA per unit? Somebody tell me. The same, right? You are per unit, doesn't matter if you're in the primary or the secondary. You're in the high voltage or low voltage side. So VA per unit is the primary of this transformer. So this one is going to be 0.9550 per unit. Right? Now, and the angle is 0 because what? There is no load, right? Let's just call it here. You just give it a name. What do you want to give it a name? I load. I load. How much is the I load before fault? Is 0, right? It said it's no load, right? I load is 0. Now, there is no circulation current. There is the IG1 here, and there is the IG2. How much are IG1 and IG2? This current is 0, right? This current is 0, right? And there is no circulation current. How much is the IG1, IG2? This is all for pre-fault. How much it is? 0. So, if IG1 is 0, IG2 is 0, how much is the VG1 and VG2 before fault? How much they are?
0.955.
They are equal to VA, right? So it's going to be 0.955. Right? This is the before fault, right? Now fault is happening. See, think about it. Reality, what is going to happen? You have two generators connected to this bus bar, and suddenly you short the second. In reality, when you put short circuit means you are putting big load on the generator, right? If you look at the generator, what is going to happen? Generator, the mechanical power is the input, electrical power is the output, right? If you look at the generator, let's say this is the shaft of the generator. So we have a T mechanical torque, and we have an electrical torque, always opposite of each other. And this is the generator speed. In generator, mechanical torque is going to rotate the machine, right? Electrical torque is going to oppose with the rotation, right? Now think about it. Electrical system, they are much faster than the mechanical system, right? If this is a real generator, either it's a steam generator or it's a hydro generator or whatever, even wind turbine, right? So there is some mechanical power coming in, right? You are controlling that. Suddenly this one becomes very big, right? Short circuit, right? You are sucking a huge current, right? So what is going to happen in reality? The generator speed is going to go up, right? Because this TV is going to get much bigger than TM, right? the machine is going to drop, the speed of machine is going to drop. But for calculation, especially during the sub-transient, is a the first cycle, very short time, right? This machine has some inertia, right? Is rotating. For the very short time, the speed is not going to drop, right? If you look at it in the long span, the speed is going to drop. But if you go just focus on the sub-transient, I'm going to calculate the worst case current, right? I'm going to go to look at one cycle, first one cycle. The speed is constant, still the speed is not changed. If the speed doesn't change, the back EMF is going to be fixed. Back EMF in general is proportional to the speed. This voltage I say here is 0.955 per unit. That's the EAF. Remember the model I put for the generator is there's the E and X, right? The EAF, they call it back EMF. That back EMF is proportional to the speed. For the sub-transient, see? Here it gave me X double prime. Because he wants to calculate the worst case short circuit current. So I can assume the voltage of generator is not going to change. Why? Because I can assume the speed of generator is fixed for a very short time, right? This one is fixed. So the voltage is fixed. So right after the fall, still I can assume my voltage is fixed. I can use this number. This one was for the before fall, right? This one was before fall, right? I can assume right after the fall, very short time, very short time, after the fall, voltage is going to stay fixed, right? Now let's draw the circuit. Right after the fall, for a very short time. You guys here? It's going to be like this. I have one machine here. How much is this voltage? This is after fall. After fall. 0.955 with 0. 0.955 with 0. But let's put the new value for xg1 and xg2. xg1 and xg2. So we calculated it before fall. What should I write now? Let's put it there. How much is the xg1? Somebody tell me. How much is the xg1? New xg1 in the new periodic system. Let me write the V base and those things here. Let me write them here. How much is the V base here? 66 and 90 units. How much is the V base here? Here. It's going to be 11 and 90 MPa. Right? S doesn't change, right? Everywhere is the same. But the voltage over there is 66, on this side is going to be 11, right? Now, look at these values. This period is in what base? In this base, right? This period is in this base, right? We are here, right? I should bring it to this new system, right? How much is the xg1? xg1 new is going to be xg1 old. How much was the old one? 0.25, right? 0.25 time V base old divided by V base new. new? 90 MVA, right? How much is the S base old? How much is the S base old? Somebody tell me, how much is the S base old? 60. So this is 1.5 times this. I don't know, you calculate. Xg2 is going to be the old value times how much is the V base old? 11 kV, right? How much is the V base new? 11 kV times S base new divided by S base old, right? So if I'm not wrong, it's 22. And this one is only 0.75. How about the transformer? Do I need to change the calculate the new value for the transformer? New XP or not? Do I need? Do I need to calculate the new for the transformer? No. Why? Because it's the selected value there, the transformer rating, right? So basically, it's gonna whatever it was. So now I'll draw it. Here I'm gonna have a J 0.375. This one is gonna be J 0.75 connected together, coming to a transformer. How much was the transformer? Point 0.1, J 0.1, and here is short, right? So basically, this is a I short circuit, and this is the IG1 after fault, and this is the IG2. This is a very simple circuit to solve it, right? You guys can solve this circuit. If you solve this circuit, if you solve this circuit, IG1 is going to be and IG2 so we calculate the IG1 and IG2. How much of the real current? If you solve this circuit, you know how we can solve it. You know that, right? How we can solve this circuit? Just put the Thevenin of this part, right? Two sources between series impedance. We can solve that, right? So try this one. It's very simple. Now I calculate this one in the per unit values. I want to know how much is point. You said 2 per unit. What does it mean 2? How many factors? How much is the I base here? How much is the I base here? Okay. How much is the I base? It's going to be S base over the square root of V base, right? It's going to be I base is going to be 90 over is the oh yeah 90 MVA. Is real current. IG1 is going to be 1.819 times how much? And IG2 is the IG1. We're going to stop here. Look at the homeworks number 6, you have, especially problem number 1 and number 2, they are very simple. If you want to practice something with the information you have, you can do. In the homework number 1, number 6, I state only, I think in problem number 1 and number 2, just draw the impedance of the system, impedance diagram. Just draw this. I haven't asked you to calculate any current, anything. Just draw that one in the new pyramid system. You read the question, you can see, you say, okay, how much, select the base value this much, and calculate the pyramid value for the system. This is the basic. So learn the basic, and after that you can start to do calculation. Problem number 1 and number 2 are pretty simple. Any questions?
When will homework 5 be due? When is homework 5 due? Tuesday?
Next Tuesday.
Okay.
And now homework number 6 is due the Friday of the week after.
Okay.
The last day of the regular quarter. The last day of the fun phase,